Okay, so we can write an accumulation function for any quantity. We don't have to go and lecture and go through all these different quantities: population, mass. Uh, we did some volume problems, but any quantity we can write its accumulation function if we know the rate. And so you're practicing that aspect of it in the homework as well. That it's a quantity we didn't talk about in lecture, but you can still do it. You can still do it. Okay, and so you practice that. You're practicing an unfamiliar quantity, but it's the same. It's the same approach. Okay, so that's due Wednesday morning. Any questions about that? Okay, so let's continue talking about work, and we're going to talk about like lifting things today. So we talked about pushing. We had the ant pushing the seed, and so lifting also requires work. So let's talk about that. I don't know where that is. I thought it was there. Yeah, there it is. Okay, here we go. So the force of gravity. The force of gravity on an object is its weight. Let me try this again here. Some weirdness going on there. Okay, what is the force of gravity on an object? What is the force of gravity on an object? I kind of gave it away there. The force of gravity on an object is the object's weight. Or in other words, you've been talking about weight all your life, right? So the weight of something, the weight of an object. What is weight? Well, weight is force. Weight is force. It's the force of gravity pulling down on that object. Okay? So weight is force. It's a force towards the earth, right? It's the force of gravity on that object. Okay? So alternatively, an object's weight is the same as the force required to keep the object from falling or to lift it steadily. Okay? So in order to hold something up or to kind of push it up gently, you have to push with the same force as the weight force pulling it down. Okay? So an object's weight is the same as the force required to keep the object from falling or to lift it steadily. Really important. Okay, so thus the weight has force units of newtons or pounds. Okay, and I already introduced these facts, right? This was facts, knowledge. I introduced you to these facts right here on the quiz over the weekend, and I told you that for metric, force has units of newtons, and in the English system, force has units of pounds. Okay? It's not anything else. So there's only one force unit in each of the systems. Newtons in the metric system, pounds in the English system. So other things like Newton meters and foot pounds and joules and all these other things are not force units. They're not force units because newtons is a force unit and pounds is a force unit. Okay? And so both of those could measure weight because they're force units. Both of those would be the units on the weight of an object. Okay? What about kilograms? Is kilograms the weight of an object? No. This is the confusing thing because in our daily life, we converse and we see things on food packages in the grocery store that say grams, and we converse about kilograms as if it was weight. This is the confusing thing. But when we're talking about science, we're talking about technically or truthfully, kilograms is not weight, it's mass. So kilograms is not the force pulling on it, but just the amount of stuff. Kilograms is just like how much stuff, regardless of any gravity pulling on it. Okay? So pounds and newtons are weight units or force units. Kilograms is for mass. Okay, kilograms is for mass. So weight force is calculated by F equals mg, where m is the mass of the object and g is the acceleration of gravity. So if you have the mass and you want the weight or the equivalent force, then you're going to multiply that by the acceleration of gravity. So m times g gives you force, and if you're talking about in the context of weight, it will give you weight force. Okay. So in problems, if you're given the mass in kilograms, if you're in the metric context, you're going to use the mg to calculate the weight force. Okay, but what about if you're in the English context and you're given pounds? How do we get the weight force from that? Well, there's nothing to do. Pounds is already weight force. So there's no initial calculation to do like you might have to do in the metric system where you're given kilograms. Okay? So in the metric system, if you're given kilograms, you have to do this kind of initial step to calculate force or the weight in newtons. But in the English system, if you're in the English system and you're given pounds in the problem, then there's no calculation to do. It's already force. Pounds is already force. Okay. Questions on that, all of that? Did that make sense? Any questions? So one more time, there's only one unit of measure for force in the metric system, and that's newtons. And there's only one measure of force in the English system, and that's pounds. And so newtons and pounds are our two force units. And so if we're talking about weight, weight is a force, you're going to use those units for weight. Okay, so let's do an example. There it is. Okay, we're going to do this example. And it says a winch lifts a platform from the ground to the top of a building by a thick cable. Here it goes. All right, so the rate of change of the cable weight is 151.77 newtons per meter. The platform structure, including people, weighs 2,815 newtons. So the winch, winch is just this this thing that's like a coil. It coils up the cable and it rotates to pull the cable up. Okay, and as it does that, then the cable wraps around the winch. Okay, so the winch must lift the floor of the platform 93 meters for the people to step out onto the building's top. So we're going to define a function W, whose value is WH, give the accumulated work at each height h above the ground as h varies from 0 to 93. Okay, so let's talk about understanding the problem and modeling the problem, and don't jump so quickly into numbers and formulas and trying to crank out an answer. So let's talk about what are the key quantities involved here. So if we read this and we know that the winch is pulling the thing up, it's going to require work to pull up the platform. So let's just kind of first write down what are all the key quantities. And by quantities I mean temperature, distance from home, or things like that. So what are the key quantities in this scenario that's going to help us figure out the work?
The rate of change of the weight of the cable.
Okay, so, and what is that? So that's kind of a weird way to say that. The rate of change of cable weight. What's maybe a more
tension.
Okay, tension. So it's talking about the cable weight. So
Force acting on the cable?
No, it's just talking about the cable itself. It's not talking about, it's isolating the cable away from everything else and just telling you a property of the cable. Okay? So
we would use that as like a constant to add on to the actual accumulation function, wouldn't we?
No, because what does this mean that it's newtons per meter?
Oh, like it constantly changes?
It means that as you roll up the cable, it weighs less and less.
Okay, that's true, but it's still it's out of the context. This quantity it doesn't have anything to do with the winch. It doesn't have anything to do with the platform. It's just a quality of the cable.
I just look at it graphically when I see units like that, so that's how I make sense of it. I don't know if that's right.
So it's really just saying how much the cable weighs every meter. So like if this cable was laying on the floor or you know it was like on the shelf at Home Depot, it's just talking about how many newtons does every meter of the cable weigh. So it's like the unit cable weight. Does that make sense? It's just like how many newtons does each meter of cable weigh? So that's a quality of the cable irregardless of the situation. Okay, so what other quantities are involved in this situation? We've got the unit cable weight. What else?
Wait, does that mean how much force is in each meter of that cable? Like,
Yeah, yeah. If you had a meter of this cable and it was sitting on the table, then the force on that would be 151.77 newtons down, and the table would be pushing back with 151.77 newtons.
and that doesn't calculate gravity or anything? Like does that have gravity calculated in it?
Newtons is a weight measure. Yeah. So yes. So by saying that the cable weight is gravitational force. So that's what weight is. It's the force of gravity on the object. So if the force of gravity pulls on 1 meter, every meter of cable with 151.77 newtons of force. And that's the weight of it. Weight of 1 meter.
Okay, got it. That makes sense.
Does that make
Thank
sense?
you.
Cool.
Yeah.
All right, what other quantities are involved here?
The platform structure, including the people, weighs 2,815 newtons.
Okay, so the weight. So and again, and to clarify what I mean by quantity, a quantity is not a value. So a value would be a measure of a quantity. So a quantity is something like the temperature in this room, the distance from my house that I've ridden on my bike. So it's a quantity takes on values, but the quantity itself is not the value of it or the measure of it. Okay, so but yes, the weight of the platform, and I think so we can platform plus the people. We can put that all together. Okay, what other quantities are going to be important here?
The height above the ground.
Okay, good. So the height of the platform above the ground, that's going to be important. Keep going, doing good.
The work?
Oh, sure, of course. The work done by the winch. Certainly a key important thing here. So related to the height, so let's label that. So right now I'm showing the height as this right here. Does the height give us something related to the weight on the winch? Directly? Or is there something else that's related to the actual weight on the winch?
Gravity. Like,
Okay. All right, so the acceleration of gravity.
Oh, the higher the platform, doesn't that mean that the winch has done more work?
Okay, that's true. Yep, that's right.
Yeah.
But this quantity right here, this height, the value of the height, is that directly helping us figure out the work?
Do you need to know the force acting on the platform and the cable?
Yes, right? Because what we're going to do, if we're doing a work accumulation function, we need the rate of change. What's the rate of change of work? Force. Remember that from last time. Super important. The rate of change of work is force. So the force on the winch.
Wait, force on the winch, is that like the platform going down on it, or how fast the winch is like curling the...
No, it's the force pulling down on the winch.
Okay, alright, I wasn't sure which one.
Okay, so there's another really important quantity here, and it's kind of related to the height, but it's not the height. The height is not going to directly get us the work, but the height is super important. What's that?
How much cable there is left?
Yeah, so the length, right? So the current length of the cable. Okay, let's see. Anything else that you think will be important here for coming up with our WH function? Okay, so now let's talk about which of these quantities are constant quantities in the situation, which we call parameters. A parameter is there's constants and parameters and variables. All right, so constants are the same no matter what situation you're talking about. Parameters stay constant in the given situation, so they're not going to change for us. But if we had a different winch and a different platform, those might change. And then variables are going to vary in this situation. So as this situation unfolds, those quantities will actually change. So do we have any constants? Do we have any constants? Things that never change.
The acceleration of gravity.
Yeah, so this one would be a constant. Okay, what about parameters? Things that stay constant, stay the same value in our situation, but might change if we had a different winch and platform and cable.
The weight of the platform, like the people on the platform.
This is a parameter, so it stays constant in our situation. What about the unit cable weight? Changing or constant?
Parameter, right?
That's another parameter. Okay. Height of the platform. Variable? Or
Variable.
definitely variable, right? Definitely variable. How about the work done by the winch?
Is that a variable?
So when we talk about work, we're always the implication is accomplished work, right? How much work accomplished so far? And this is
But
a
that
big
would change throughout the situation.
Yeah, well, here's the big hint, right? We're writing a work function. That's the whole point of a work function, is that based on the height, the accomplished work, how much work done so far, is changing. For sure, that's a variable. Okay? What about the force on the winch? Is that staying constant as this thing moves up, or is it changing? The downward force on the winch. So does the rate of change of work, does the rate of change of work stay constant, or does it change?
Would it change because unit cable weight can change with length of cable?
Okay, right. So the cable's getting shorter. Someone said this before, and then again now. The cable's getting shorter, and when the cable gets shorter, the weight force of the remaining cable is going to be less. So as that thing goes up, that the force on the winch due to the cable is decreasing. So that's a variable. So, and again, that makes sense. If we're doing an accumulation function and this is our rate of change, so normally the rate of change changes. In this case, it changes. The rate changes because of the remaining cable length, which is always changing. So then the force on the winch is like decreasing as it goes up. Does that make sense, everybody?
Yep.
The force on the winch is maximum at the bottom because you have the most weight of the cable, but now the cable's getting shorter and shorter, and so there's less weight from the hanging cable as it moves up. Okay, what about the length of cable remaining? Variable or parameter?
Variable.
Variable. Okay, so we're understanding the situation here. We're modeling it. We're talking about the quantities. So now we're gonna let's write some symbols to model this, right? So length of the cable. What do we want to call that? And that'll be in what? In meters. Length of the cable in meters, which I was showing in my illustration here. We'll call that L for length. So right there. I'm going to pause live here for a sec. So length of the cable we'll call L. And then what about the force on the winch? What symbols? Oh, and so let's go next to, we've already got some symbols ready for us here. So the height of the platform, they're calling little h for us. Okay, so length of the cable we'll call big L. Height of the platform will be h. What about the weight of the platform and the people? So since that's a parameter, since it's a known value, we don't really have to assign. We don't have to assign a symbol to it. We just have its value. So that we know is 2815. The unit cable weight, again, we could assign a symbol to it. We don't need to. It's the 151.77. What about the work done by the winch? What symbols do we have for that?
W
W
of H.
of H. Okay, so we got W of H, H. So what would the rate of change? What would the force on the winch be then? How are we gonna symbolize the force on the winch?
RW of H, like the rate of work.
Yep, that's it, right? So the force on the winch is going to be this variable force. It's going down as the cable goes up because there's less cable weight for every moment that the thing moves up. And so that's the rate, and we know the force is the rate of change of work. So we got R sub W of H. And so I think we've got everything. Acceleration of gravity is already G, and that's 9.8 meters per second. Now, will we need that in this problem? Look at how everything's given. My unit cable weight is given in newtons per meter. The platform and the people is given in newtons. Do I need the G?
Because you don't have any masses that are given to you.
Yeah, so we would need the G in the calculations if they gave us everything in terms of mass. If they gave us the weight of the platform, or the mass of the platform, the mass of the people on there, then we need to multiply by the 9.8 to get newtons. But they just gave us newtons from the start, so we're not going to need that. We're not going to need the 9.8. Okay, so let's see. So now we want to come up with this. So basically, if we want the work accumulation function, we want the force on the winch. That's the rate of change of work, right? If you need accumulation, you need the rate of change. So we're going to write the force on the winch now. Can I erase what I've written so far? Okay.
Wait, so variables? Oh no, it's fine. No, for
Oh,
the
go ahead.
variables, since there's 4 of them, wouldn't we have to define them in terms of one, like the height, or the length of the cable? Wouldn't we have to use that one to define the
Yes.
other
Yeah,
three?
that's what we're going to do. So we're doing the rate of change
Oh,
of
okay.
work with respect to, we're going to do H, because that's what they're asking for us here. They're asking for a work as a function of H. And so, yes, that's what we have to do. So what is, so this is force on the winch. So we got H and we got L. So what's going to be the structure of the force on the winch? How am I going to get the amount of force on the winch? What will be the overall structure of that function?
Mass times the gravity. Yeah.
Okay, so like we talked about, we're given everything in weight units. We're not given kilograms. So we don't need that initial step of mg. Does that make sense?
Oh.
We're starting off. So yes, if you were given kilograms, you would have to do this. You'd take your kilograms, multiply by g, and then you'd get force. But we already have force, right? We already have all our units are already in newtons.
Would force be a linear function depending on the length of the cable?
Okay. So we're gonna a linear function. So it can be more specific. Like how are we gonna get, say, at height h, length l, what, just in general, like is it gonna be like division or multiplication, or like what's gonna be the overall structure of this function before we start writing down the formula? Like what are we thinking? How are we gonna compute the force on the winch?
Would there be addition of the weight of the platform and the weight of the cable?
Okay, and she's onto something. We're gonna have the weight of the platform with the people.
Yeah, with the people.
Yep. And
And the weight of the cable.
weight of the
Force
cable.
on cable.
So here's the overall structure of our function. We need the weight of the platform, or the force of the platform and the people, the gravitational force, and then the gravitational force of the cable. All right, so now we got two things to do. What about the weight of the platform and the people?
That would be 2,815.
Given. Half done. Okay, so what's the weight of the cable? What's the weight of the cable? Is that constant or changing?
Changing.
Changing, right? It's changing. And so how do we get what it is? So it's like, and we need it to be a function of h, right? So here we are. It's h above the ground. That means that there's L, and this was 93.
Is it 93 minus
You
h?
can represent L.
L is, someone said 93 minus h. Agree with that? Does that make sense?
Yeah.
Yeah, the amount of cable left is going to be the 93 minus whatever height we've moved through so far. So we're going to take 93, the whole height, minus the height so far is going to be what's left, length of the cable. All right, good, making progress. So we know we have 93 minus h length of cable. How do we get the weight of that amount of cable?
Multiply by unit cable weight.
That's it. So this is meters, and this tells us how much each meter weighs, right? We need the total weight of that much cable. Each meter weighs 151.77, and we have this many meters left, right? Hanging down. So we're going to take 151 times that number of meters. Okay. What do we think? Are we finished? Are we finished with the rate function, the force? Is there any other things making causing forces, a downward force on the winch? Anything else?
The force that's, I guess, keeping the winch down from the gravity is the force, the weight itself, right?
The weight of the winch?
Yes.
No, so
Or the cable weight?
the winch is held up by on the top of the building, so that the winch, like, it's attached to the top of the building, so its force is counteracted by the roof. Does that make sense?
I see. Yeah, that makes.
Yeah. Okay, so that's it. So now we can write our work accumulation function. And it's going to be, we got a rate of change. It's a changing rate. Why? Because the cable is getting shorter, and so the weight of the cable on the winch is decreasing. And we're going to use T now. Right. And so how do I write the work then? You're all thinking it, right? Integral, right? Integral. So then let's use our good to. So what do you say? A comma H. And so then this could be like from any initial height so it'd be all no, if we do A comma H, then that's just the net accumulation of work. Starting from any point A. Okay, and then dt. All right. Any questions on that? Did we write the work function?
Yep.
Okay, so what's half of 93? 45, 46 and a half? So, how about this amount of work versus this amount of work? Are they equal?
No.
Someone's saying no. So what does this represent? This is the work done to pull the platform from the ground floor halfway up. And then this is the work from halfway up to the top.
Yeah.
Equal amounts of work?
No.
Okay, which do you think is greater?
W. W0 to 46.5.
He's saying this first one is greater than this one. Rest of you agree with that?
Agree. Yeah.
Yeah.
Yeah, because why?
Because the unit cable weight is higher in the bottom half than the top half, so there's more force acting on that, and so a higher rate of change, so meaning more accumulation.
Right, exactly. The total weight of the cable is more in that bottom half, right? Because we have the whole cable extended, and then half the cable extended. So the work to pull that up is going to be more because we got longer cable in the first half, shorter cable in the second half. So we would
Mark, can I
expect.
cut in for a second?
Yeah, sure.
I think I heard him say that the unit cable
Yeah.
weight was different.
So yeah, it was a small enough error that I
Okay,
didn't correct it. Yeah. So what he meant to say was the total cable weight. The unit cable weight stays the same. It's this value here, but the total weight of the cable changes, right, in the first half versus the second half. So we could correct that and say Erase. Looking right at it. This is greater than. And does that make sense to everybody? The accomplished work for the first half would be greater than the second because you have more cable weight in the first half, requiring more force, which means more work.
How were we determining that there was more cable weight in the first half? Looking at the rate of change of cable weight.
No, I'm just looking at the, it's easier just to look at the picture. In the second half, the cable is shorter the whole time, right? To 0. In the first half, it's much longer.
I see, so there's more work being done in the first half
Yep.
until we reach that point.
Because
right?
the force is greater, right? So the force, the weight is greater because there's more cable, so more work.
Right.
More force means more work.
I see. Thank you.
Okay. Any other questions on this problem? So just want to quickly look at one more example of emptying a barrel. And so we know that we can put this in GC and we can answer all kinds of questions about accomplished work throughout the process. We've done this many times. We put our integral function in GC, and then we can use function notation to crank out amounts of work. Same thing as we've been doing. All right. So let's just talk about this example here. So a barrel filled with crude oil has a density of 825 kilograms per meters cubed, and a diameter, the oil has that density, and the diameter of the barrel is 570 millimeters, and a height of 850 millimeters. How much work in joules is required to pump out all the oil out the top of the barrel? Okay, so I made a little chart here, or a little transition of equality here. So the rate of change of work we know is force, right? And the force is going to be the weight of all the oil down to a depth of x. So let me draw the barrel here. It's all filled up with oil. And so we're going to consider our frame of reference being the top. And we're going to say that, so x is going to vary from the top downward. Okay, and so the force on x depth of oil, right? The force on x depth of oil is going to be the weight. It's going to be the weight of that depth of oil. And so how do we calculate that weight? We have a density, we have a mass density. So we're going to need weight density. How are we going to get from mass density kilograms to weight density? What do?
By volume.
Nope.
Multiply by the acceleration due to the force of gravity.
Yeah, this is where we're going to use the mg, right? So this is where we're going to multiply by the 9.8, and that will give us weight density in newtons per meters cubed. And then we're going to take that weight density and multiply by the volume, and we'll get the weight of that. And that'll be the force associated with the work to get this, get that much oil out, okay? Or actually, it's associated with the work to get the thin layer at the bottom out, okay? So let's set it up. So our rate function is, so the rate of change of work for x depth is going to be, what's the volume? So what's going to be the volume? It's going to be pi r squared. What's the radius? The radius is going to be half of 0.57. So 570 millimeters. 570 millimeters is 0.57 meters divided by 2. So pi r squared times the height. What's the height?
0.85.
X, right? That's x. So this is the weight of, or the force of x depth of oil, and then we're going to multiply by our weight density, which is going to be the 825 times 9.8. So volume of that times the weight density in newtons per meters cubed, and that's going to be newtons then. So newtons per meters cubed times meters cubed gives newtons. So there's our rate of change of work. It's the force. The force is the weight associated with that depth of oil.
My pharmacy prescription.
And then we could write the work function.
Fucking Mason Dyke. He's literally the reason why I hate
Hey,
Detroit.
Spencer. Spencer, your microphone is on. All right, and so we're going to go from A to X of. I think you can do it. So you got the rate. We got the rate function. It's the force, which is the weight of this much oil. And then you can set up the work function, and that will give the accumulated work to get X depth of oil out. And so then if we set X equal to the total height, it'll be the work to get all of it out. Okay, so we'll end it there so you can take your quiz. Any questions about this?
When will the recording of this class be posted?
I try to get them up later in the day.
Thank you so much.
Okay. So this will be R sub W of T, dt. And what about this for half the work? So will X going down to half the depth give half the work, less than half the work, or more than half the work?
Less than.
Less than, right? The stuff at the bottom is going to take the most work to get out. It's got the furthest distance to go. So the first half, the work associated with half of the depth is going to be less than the work associated with the bottom half.